Hello and good afternoon friends, welcome to the CEC Reset live lecture. Dear friends, as you know that we are carrying a series on chemical thermodynamics, and so far we have conducted a numerous session under this very series. Dear friends, in our previous session we talked about entropy change as a function of a state function. Today in this session we are going to discuss on entropy change and third law of thermodynamics, and for this very discussion, dear friends, we have again with us in our studios Dr. Amit Kumar. Dr. Amit Kumar is Senior Assistant Professor in Department of Chemistry, Dayal Singh College, University of Delhi. So dear friends, without wasting any time, I would like to welcome our guest Dr. Amit Kumar, under whose able guidance we are going to understand our very topic, that is entropy change and third law of thermodynamics. So welcome to the Reset lecture, sir.
Thank you very much, Kitika. Dear friends, first of all I wish very good afternoon. As has already been briefed about what we had covered in the previous lecture, let me give you a brief introduction what we are going to cover in this lecture. In this lecture, our first emphasis will be to see how the entropy change can be quantified in relation to changes in temperature and pressure, as we have already done the same thing for variation in temperature and volume. Following which, we would also try to see the quantified change in entropy is practically dependent upon temperature only for condensed phase systems, with the help of appreciation of numeric data on the same problem, following which our emphasis will be on quantification of entropy, that is for the ideal gaseous systems. And we would like to see the equations so developed so far, how they get simplified for ideal gases, because for the gaseous systems the quantification of entropy is very important. So therefore, with these objectives, and we would like to stress upon also on the third law of thermodynamics and what help it renders basically in the calculation of absolute entropies of substances. So on that note, let us have a recapitulation of that same aspect of entropy change as function of temperature and pressure. Now we can consider entropy as function of temperature and volume, we have already considered. When we consider entropy as function of temperature and pressure rather than volume, then we can write the change in entropy as function of temperature and pressure, the partial differential in terms of temperature and pressure multiplying with temperature pressure changes. As already been conveyed that we have already derived the fundamental equation of thermodynamics that relates that is basically a combination of first and second law of thermodynamics, and that relates the change in entropy with respect to change in internal energy and the volume. Now idea is that we should have in this equation we should have the change of temperature and the change of pressure instead of change in internal energy and the change in volume. So as we can compare the two equations and we can get to evaluate the partial differential coefficients delta S by delta T at constant P and delta S by delta P at constant T in equation 35. So in order to do that, let us see how we modify our fundamental equation of thermodynamics, that is equation 11. In order to do that, we have already seen that enthalpy is basically a function of internal energy and the pressure volume terms. So therefore, we can differentiate it, and what we get is dH equal to du plus pdv plus vdp. We can modify this equation, we can take pdv and vdp terms to the other side and it becomes du equal to dH minus pdv plus minus vdp. So now we have got the value of du in terms of dH, dv and dp, and dv and dp here are important. We can see here du equal to dH minus pdv minus vdp. If we substitute this equation, equation 38 in equation 11, that is fundamental equation of thermodynamics, what we get is ds equal to 1 by T the same, instead of du we can substitute dH minus pdv minus vdp, then the second term plus P by T dv. Now we can straight away multiply 1 by T with each term inside the bracket and we can open it up. What we get is 1 by T dH minus 1 by T P dV minus 1 by T vdp, then second term plus P by T dV. So therefore, we can see over here P by T dV, these two terms figure in with the same value, same magnitude, that is P by T dV, but having opposite sign. So we do cancel each other. So, these two cancel each other. So, thereafter what we end up with is ds equal to 1 by T dH minus V by T dP. Now, we all know that change in enthalpy, infinitesimal change dH can be made equivalent to, as we had already derived, as Cp dt plus delta H by delta P at constant T dP. If we therefore substitute the expression corresponding to dH in equation 40, what we are going to have is, when we substitute equation 41 in equation 40, then what we get is 1 by T is same. Instead of dH, we substitute Cp dt plus delta H by delta P at constant T dP, and then bracket close. Then second term, this one minus comes up over here, minus V by T dP. So, ultimately we get equation 42. In this equation 42, we can further open it up by multiplying 1 by T term in both these terms. What we get is ultimately Cp by T dt plus 1 by T delta H delta P constant T dP, then minus V by T dP. And therefore, we can take dP common out of the second and third term in equation 43. What we get is 1 by T over here as common, then we end up with minus V over here this term plus delta H delta P constant T dP. So, therefore, now we get equation 44, wherein we have the change in infinitesimal change in entropy at the left hand side, also in equation 35, which we had envisaged entropy as function of temperature and pressure. Here also we have written infinitesimal change in entropy ds to the left hand side. To the right hand side of both these equations, there are differentials dt and dp appear. Here also dt appear, here in this equation also dt appear, dp appear here also, as well as in equation 44. So, therefore, it means the differential coefficient this and Cp by T should be same, and differential coefficient delta S by delta P at constant T should also be same as the 1 by T times this bracket term. So, ultimately by comparing these two equations, what we get is these further equations, that is delta S by delta T at constant P. This is one of the differential coefficients in one equation, and this is the differential coefficient in the other equation with same differential dt. So, in this manner we evaluate the differential coefficients delta S delta T constant P and delta S delta P constant T. The first one is very simple to evaluate, because in the right hand side you can see we have only the heat capacity at constant pressure and the temperature. Both these are experimentally measurable quantities, and one of them is state function as well. Coming over to this equation 46, if we see 1 by T, the temperature and the volume is very simple to evaluate for a system, but evaluating delta H by delta P at constant T requires the experiment to be performed on the lines of Joule-Thomson experiment. So, therefore, this equation needs further simplification. So, this equation also how we can make use of to calculate change in entropy with respect to change in temperature, the equation 45, we can also see that. You see over here, we consider first of all equation 45, ds by dt at constant P equal to Cp by T, which we can rearrange this equation, we get ds equal to Cp by T dt. That is, we can take dt from the denominator of left hand side to the numerator of right hand side, and ultimately if we want to quantify this entropy, that is, if we want to calculate the entropy change for a particular change in temperature, then we need to integrate this equation 47 within limits the temperature range T1 to T2. So, what we get is the left hand side we get after integration of ds we get delta S, which is equal to integral within limit T1 to T2 Cp by T dt. Now, if we consider that this heat capacity at constant pressure is independent of temperature range, which we have considering, then we can take Cp out of this integral, and then we can integrate dt by T within limit T1 to T2, and what we ultimately get is delta S equal to Cpl and T2 by T1. But if we consider that Cp is not independent of temperature within this temperature range, then we have to write the Cp in terms of logarithmic, in terms of power series, and then we have to integrate this whole equation in the form of different parts of the power series. Correspondingly, this equation therefore is very easy to evaluate, and therefore equation 49 determines the change in entropy by virtue of the change in entropy by way of increasing the temperature from T1 to T2. So, this equation 49 quantifies the entropy change for a particular change in temperature. That is why I said evaluating of this first equation, equation 45, that is first differential coefficient using which evaluation of delta S entropy change is easier. But if we want to make entropy quantification of entropy change using equation 45, instead of 45 the 46 for a particular change in pressure rather than the temperature, then we need to simplify equation 46. In order to do that, what we go to do is we first of all consider again the same equation 45, that is the one of the differential coefficient delta S delta T at constant P, which is equal to Cp by T. What we do is we differentiate equation 45 with respect to pressure at constant temperature. Then what we are going to have is we will differentiate it, this differential coefficient, but not now with temperature but with pressure. So, it means first we are differentiating entropy as a function with respect to temperature at constant pressure, and then whatever we get as a result of this differentiation, we differentiate this result again with respect to pressure, but now at constant temperature. So, therefore, what it means is this, to evaluate this we should differentiate Cp by T with respect to pressure at constant temperature. So, therefore, what we write is 1 by T, considering temperature is constant. So, therefore, 1 by T del Cp by del P. So, which is equal to 1 by T in bracket del by del P. Instead of Cp, we know by definition of Cp we have delta H by delta T at constant P. So, we just substitute this value. So, what we ultimately get is we can write this differential coefficient, double differential, in the form that delta square H by delta P delta T. So, ultimately we get equation 52, that is delta square S by delta V delta T, which is equal to 1 by T delta square H by delta P delta T. So, now exactly the treatment which we have done for equation 45, it is now time to do the same treatment to equation 46. That is, now in equation 46 we have differential coefficient, which is basically the differentiation of entropy with respect to pressure at constant temperature. So, if we want to get the double differential, then we need to differentiate equation 46 with respect to temperature now, but at constant pressure. So, what it does mean, we will get as the left hand side delta square S by delta T delta P, which is basically nothing but the fact that we have taken the entropy function, we have differentiated first it with respect to pressure and then with respect to temperature at constant pressure. So, therefore, it means if we want to get a result for this double differential, this is the first differential. So, therefore, we should differentiate this right hand side of equation 46 with respect to temperature at constant pressure. So, we can write del by del T in within bracket we can write this whole expression 1 by T minus V plus delta H delta P constant T and at constant pressure. So, therefore, this is equation 54 which we get. Now, we can differentiate it. In order to differentiate it, we are differentiating this whole term 1 by T minus V plus delta H delta P constant T with respect to temperature. So, here we can consider that 1 by T as one function and minus V plus delta H by delta P at constant T as another function. So, what we will do is we will write first of all the first function 1 by T as such, and we will first of all differentiate this term within the bracket, that is minus V plus delta H delta P constant T. If we differentiate this bracket term with temperature, what we are going to have is, let us see, if we differentiate delta H by delta P at constant T with respect to temperature at constant pressure, we are going to get delta square H. If we differentiate this term with respect to temperature, then we will get delta square H delta T delta P. Then minus, because this is volume which has minus sign, so minus sign comes as it is here, and when you differentiate volume with temperature, you get delta V delta T constant P, right. So, therefore, what you get is this term. Then you will differentiate you will write this bracket term as such, that is minus v plus delta h delta p constant t, and you multiply with differentiation of 1 by t, which is that is minus 1 by t square. So, you just write it is here. So, thereafter what you can do is you can expand the terms by multiplying 1 by t with this whole bracket term and multiplying this, just writing this second term as such. What you will get is 1 by t del square h del t del p minus 1 by t delta v delta t constant p minus 1 by t square and the bracket term. Now, you can see over here, here also this is one equation we have got, that is delta square s by del t del p. Similarly, we had derived equation 52, that is delta square s by delta p delta t. So, we have just written both these equations. This equation 52 has come from the earlier differentiation of delta square s by delta s delta t constant p by differentiating it with respect to pressure, and this term has come, this equation 56 has come by differentiation of delta s delta p constant t with respect to temperature at constant pressure. So, therefore, now we have these two equations 56 and 52, we can compare the two equations by virtue of Euler relation, which say that if there is a state function, for example f, then delta square f by delta x delta y, which is same as equal delta square f by delta y delta x, that is the order of differentials are immaterial, the same. So, left hand side is being the same. So, we can, while we can compare the two equations, we say that right hand side are equal. So, we just equate the right hand side of two equations. What we get is delta 1 by t delta square h delta p delta t equal to 1 by t delta square h delta t delta p minus 1 by t delta v delta t constant p minus 1 by t square minus v plus delta h delta p constant t. What we are going to have is, because this order of differentiation is does not matter, so we can change in our next equation, we can change this order of differentiation. So, if you compare the two terms, the order of differentiation are different. So, but now here these two orders of differentiation are same, so we can cancel the two term. What we get, minus 1 by t del v del t constant p minus 1 by t square minus v plus delta h delta p constant t, that is equal to 0. We can rearrange this equation, we can take minus 1 by t square this term to the other side, what we get minus 1 by t delta v delta t constant p equal to 1 by t square minus v plus delta h delta p constant t. So, then we can cancel 1 by t from two side, we get equation 58. So, this equation 58, now we can compare it with the equation which we had written earlier, that is delta s delta p at constant t equal to 1 by t minus v plus delta h delta p constant t. This equation had been derived earlier. So, therefore, we can compare the two equation. If you carefully see the two equation, the right hand side of this equation is equal the left hand side of equation 58. So, we can say that left hand side of this equation is equal to right hand side of equation 50, this top equation. So, therefore, we come to know that delta s delta p constant t equal to minus delta v delta t at constant p. So, this equation 59 which we have got here is relatively simple expression for isothermal volume dependence of entropy. What we mean to say by this is that the temperature is kept constant and therefore, the condition is isothermal. So, isothermal, it is not volume dependence, but is pressure dependence of entropy. It is written over here volume is incorrect. So, it should be written here pressure. So, for the isothermal pressure dependence of the entropy in terms of derivative delta V delta T constant P, which is readily measurable for any system. Why this is readily measurable? We just get to see from here. The equation 59 we can first once again to the left and right hand side we can multiply and divide with volume. So, what we will get is minus V 1 by V delta T constant P, but basically 1 by V delta T constant P is just nothing but alpha, the expansion coefficient. So, therefore, we can write delta as delta P constant T equal to minus V alpha, and so therefore, we have evaluated equation 60 here. and equation 45 earlier, the earlier differential coefficient we had derived delta as delta t constant p equal to Cp by T. So, we can substitute equation 45 and 60 in this equation, that is we have evaluated the differential coefficient, the two differential coefficients, what we get ds equal to Cp by T dt minus V alpha dp. Basically this equation 61 is just nothing but accounts for entropy change for any substance which is basically relating to change in temperature and pressure. Here you can see ds equal to Cp. Cp is an experimentally determinable quantity, T temperature is an experimentally determinable quantity. The temperature change you can just determine before and after the change, initial and the final state, and minus V the volume of the system, then the alpha expansion coefficient. If you get to know the working substance of system, you can easily determine alpha is experimental quantity and dp again is a state function. So, just by determining the change in temperature and pressure and knowing Cp volume and expansion coefficient and the temperature, you can determine the entropy change of the system. Now, if you remember, when we had derived a similar expression for entropy change using the temperature and volume as two state functions. So, in that situation also we said that entropy is basically a function only of temperature for condensed phase systems, because in that situation volume change was very small for condensed phase system unless pressure is very high. Here also if you see, we can get to understand that entropy is again a function practically of temperature only for condensed phase systems, because the pressure change which we account for, that is not the pressure change term which involve two terms, the volume and the alpha, the expansion coefficient. Expansion coefficient is just a measure of how much volume change is affected by a particular change in temperature. So, therefore, at a particular this expansion coefficient, since this expansion coefficient for a particular change in pressure is small, so therefore, this term is very small and then the entropy change would be almost same as what is determined by the first term. So, therefore, we can say entropy change is practically a function of temperature only for condensed phase systems, but for gaseous systems this has a this term the pressure dependence also makes a difference over here, and entropy also depends significantly on pressure change as well. We can understand this point with the help of an illustration from a numeric data. Let us consider a numeric data. For example, let us have the same equation again, ds equal to Cp by T dt minus V alpha. Now, you see, for solids it is you can observe by the data in handbook of physical chemistry, for all the solids, for most of the solids, the alpha, the expansion coefficient is just of the order of 10 raised to the power minus 4 per Kelvin or even less. For liquids, alpha is almost similar to 10 raised to the power minus 3 per Kelvin or less. So, this is just so small alpha value. Now, suppose molar volume of a liquid. Now, we say that molar volume of a liquid is 100 centimeter cube per mole. So, molar volume is 100 centimeter cube per mole. If we do convert it to meter cube per mole, the quantity comes quantity is 10 raised to the power minus 4 meter cube per mole. Now question arises, what is the entropy change if pressure is increased by 1 atmosphere? 1 atmosphere 10 raised to the power 5 Pascal, that is if you change pressure from 1 atmosphere to 2 pressure. So, basically here dp should also be there in this equation, minus V alpha and dp here, dp is the pressure change. So, what we get is the pressure change value, we have also obtained the temperature change value. If we keep now, suppose now since this expression equation 61 determine entropy change with change in temperature and pressure. If we say Suppose that the temperature is constant. At constant temperature, if you want to determine the entropy change when a particular change in pressure, that is 1 atmosphere change in pressure is observed, then dt equal to 0, then in this equation the equation transform and you get the another equation. This is equation 62 rather, not 61. ds equal to minus v alpha dp, the first term dt equal to 0, then second term you have. Then you can integrate this equation, you get delta s which is equal to integral s1 to s2 ds, that you can obtain it as minus integral p1 to p2 v alpha dp. And if we suppose volume is just there is no practical change in volume due to a particular change in pressure within pressure range p1 to p2, you can integrate it and what you get is minus v alpha delta p. So therefore, we have the final expression as delta s equal to minus v alpha dp or delta p. It should be delta p here, and delta p which is equal to 1 atmosphere, that is equal to 10 raised to the power 5 Pascal. Thus, now the volume, the molar volume which we had determined, if you remember, it is just 10 raised to the power minus 4 meter cube per mole for liquids. Then alpha 10 raised to the power minus 3 per Kelvin, we had just observed, we have just seen the value. If you will find these values, you can find it in handbook of physical chemistry in most of the, for most of the liquids. And then this value, that is the pressure change which we have affected, then is amount 10 raised to the power 5 Pascal. That if you multiply all the terms, what you ultimately get is, by working out units, you get minus 0.01 joule per Kelvin per mole. Now what it does mean? It does mean that for 1 atmosphere change if you bring about on the system, that is, if you increase pressure by 1 atmosphere, then you will observe a change in entropy that is only 0.01 joule per Kelvin per mole. Entropy will decrease by only small, very small value. Therefore, if you want to produce a 1 unit, that is 1 joule per Kelvin per mole in decrease in entropy, then you have to produce, you will have to exert a pressure of at least 100 atmospheres on the liquid. It means such high pressures you are required to apply on liquid system to bring about a change in entropy of system by 1 unit, that is 1 joule per Kelvin per mole. So, which we normally do not work in those situations. As a result, we say entropy is practically a function of temperature only, and the effect of pressure has not much significant change on the entropy value of a liquid or of a solid substance. This is just how we can observe. If it is for a liquid, then the alpha, the expansion coefficient for solid, as you can see, I had given you shared the practical data which has been observed in handbook of physical chemistry, that is even 10 times lesser of the order. So therefore, entropy change for solids would be even much lesser than what you have actually calculated for a liquid substance. So in view of this, we can say that entropy change for condensed phase, liquid and solid substance is practically a function of temperature, not practically a function of pressure, but for real gases it makes a big difference. We can just have a look at the data itself. For example, if we bring about a pressure change from 1 atmosphere to 2 atmosphere on a gas, then the corresponding change in entropy would be, entropy will decrease by 5.75 joule per Kelvin per mole. So therefore, decrease is large. Why the decrease is large? Because there is greater compressibility of gases, and therefore the coefficient of compressibility factor will be higher for this for these gaseous subspecies. So therefore, you can observe a greater change in entropy. So it means that entropy, if you want to calculate for gaseous systems, then you must take into account the change in temperature as well as the change in pressure. but if you want to calculate for solid substance, liquid substance, that the pressure may not have that much significant effect on entropy. Okay. Having said this, now if only gaseous systems play a exhibit only a significant change in entropy by virtue of change in pressure, then all we can do is we can modify the equations for calculation of entropy change for the ideal gases, that is when applied to ideal gases. In order to do that, let us consider internal energy, which is a function of temperature and pressure. Then we can write using these partial differential delta U delta T constant V dt plus delta U delta V constant T multiplied with dV as change in internal energy. So, therefore, for an ideal gas, this also we have observed Joule law, that is for ideal gases systems entropy is just internal energy just depends only on temperature. So, at temperature there is a direct measure of internal energy, since for ideal gas volume change does not matter. Why it does not matter? Because we have considered that volume occupied while modeling the ideal gaseous systems, we have considered that volume occupied by gaseous species is very small as compared to volume of the system in which the gas is confined. So, therefore, also from Joule law delta U delta V constant T is equal to 0. With this, the equation 13 you can write it as du equal to delta U delta T constant V dt. So, but this equation, the partial differential which you have written here is Cv, therefore, so du equal to Cv dt. So, du equal to Cv dt, you can consider fundamental equation of thermodynamics. Instead of using Cv dt plus delta U delta V, you just for an ideal gas you can substitute this equation du equal to Cv dt. What you get? Cv dt in for du, then divide by T. So, Cv dt by T plus P by T dV. So, therefore, this equation represents the fundamental equation of thermodynamics for ideal gas systems. Now, if we in this equation there is another very important point which we can understand, that this equation relates to change in temperature and volume. So, we must express all the functions as functions of these two variables only, the temperature and the volume, but here the pressure comes. So, we can make use ideal gas equation where P equal to nRT by V. So, we can substitute in this equation 65 for P, you can write nRT by V. So, what you get ultimately ds equal to Cv by T dt plus for P instead of P nRT by V into T, that dV. So, T cancels from numerator and denominator, what you get ds equal to Cv by T dt plus nR by V dV. Now, idea is that this modified equation 66, that is also fundamental equation of thermodynamics for ideal gaseous systems, you can consider and you can compare this equation with that equation 66 with that of equation 12, that says ds equal to delta S by delta T at constant V dt plus delta S by delta V constant T dV. So, basically if we compare equation 12 and equation 66, so what we get ultimately? We get the values of differential coefficients delta S delta T constant V and delta S delta V constant T for which system? Now, it is important to understand the system we are talking about here is only ideal gas. Therefore, delta S delta V constant T equal to nR by V. If we compare these two differential coefficient, and when we compare these two differential coefficient, these two become delta S delta V constant T, that is equal to nR by V. So, therefore, delta S delta V constant T equal to nR by V. Now, what this differential coefficient, what kind of meaning we can understand from this differential coefficient? What the differential coefficient, the differential coefficient express the change in entropy for a particular change in volume. So, therefore, this differential coefficient, now we can see to the right hand side, it has only 3 terms. number of mole, R gas constant and volume, all these are positive values. So therefore, the differential coefficient is always a positive quantity. It means the entropy will always increase with increase in volume, will always increase with increase in volume. What this implies? It implies that the derivative is always a positive quantity, and therefore, for isothermal, for all isothermal transformations at constant temperature, the entropy of an ideal gas will increase with volume, but the greater decrease will be observed when the volume is smaller, and the smaller decrease will be observed, lesser decrease will be observed in entropy when the volume is larger. Why this is so? Because volume figures in the denominator of this differential coefficient equivalent expression. So therefore, we can now once again consider equation 66 there, ds equal to Cv by T dt, Nr by V dV. If we want to determine the finite changes, then we need to integrate equation 66 within limit T1 to T2 and V1 to V2. So therefore, delta S equal to integral T1 to T2 Cv by T dt and plus Nr integral V1 to V2 dV by V. So therefore, delta S equal to, when we integrate this equation, there we assume two things, only one thing, that is heat capacity Cv is independent of temperature range within temperature T1 up to T2. So therefore, we can take it outside and we can integrate it dt by T. What you get, ln T and ln T2 by T1 is the integral. Same way, ln V2 by V1 is the integral value for the second integral. So what you get? You will get delta S, that is entropy change, equal to Cv ln T2 by T1 plus Nr ln V2 by V1. And similarly, if we consider the change in entropy in terms of change in temperature and pressure, then we can also obtain similar expression, that is delta S equal to Cp ln T2 by T1 minus R ln P2 by P1. So these are the two equivalent expression using which we can calculate for a modeled system, that is ideal gas, the entropy change value. Once we do determine it by just, all we need for an ideal gas is the change in temperature, the change in pressure and heat capacity, and so that is it, the number of moles. So therefore, what I want to say is that for a modeled system, if we can determine entropy change in this manner, then it gives us a fair idea about what happens in a real gas. So we can modify it also using van der Waals equation of state, and we can get to know, we can get to determine what way the entropy changes for real gas in that manner also. In addition, we can also make use of various expressions being developed, such as ds which is been equal to Cp by T dt plus alpha by kappa dV. That is one expression which we have developed. We can make use of this equation that always applicable, that is always applicable for all the kind of chemical species, whether being they are solid, the liquid, the gaseous or real gases or whatever, both these equations are applicable. So therefore, but in equation 61 written over here, it should be dP also. Now you notice one point, very important point here, Cv is a positive value, temperature is a positive value. So it means if you dt increases, dt positive, then entropy ds will be a positive quantity at constant volume. It means entropy increases with increase in temperature. Coming over to second point, if temperature is constant, then first term is 0 and then alpha and kappa, both these are positive quantities, but except for alpha we have already considered, except for water within temperature range 0 to 4 degrees Celsius. Therefore, for with volume also entropy increases. Coming over to equation 61 here, this also says here dP is also there. So when dP is 0 at pressure constant, with increase in temperature entropy increases, ds positive. At constant temperature, this V is a positive quantity, alpha positive dP. If pressure increases, dP should have been written over here, but is not. So, you can consider after alpha dP positive plus all three value positive plus value. When multiply with negative sign, it means ds will decrease with increase in pressure. So, now what I wish to say is that when you increase temperature, the entropy increases, when you increase volume, the entropy increases, but with increase in pressure, the value of entropy decreases. So, these are the important consequences, important observations being made due to these equations, that is how the entropy changes with change in temperature, pressure and volume. So, it means with both temperature and volume they have same effect. By virtue of increase in these two variables, the entropy of system increase. Then on the other hand, the entropy of a system decreases with when you increase the pressure of the system. So, with this we now come to the consideration of standard entropies of substances. What is standard entropy? The standard entropy at the temperature of interest, at any particular temperature you can say, is the value of molar entropy under 1 bar pressure. So, what is the definition of standard entropy of a substance? Just standard entropy, the entropy of a substance at a particular temperature for 1 mole of a substance, but at 1 bar pressure, and is given a symbol SM standard. Now, question arises how to determine entropy of a substance at a pressure other than 1 bar pressure if standard entropy of a substance is known. Now, it is important to observe that if you remember, we had said the entropy is defined as a change in entropy. Enthalpy is also defined as a change in entropy. When we had defined internal energy, we also defined it as the change in internal energy. We said we cannot determine exact value, absolute value of internal energy of a substance. What we can determine, only we can determine the change in internal energy when a system undergoes a change, when a system transforms from one state to another. Same thing is true also for enthalpy. For enthalpy change also we can determine, but absolute value of enthalpy of a substance difficult to determine. Now, coming over to entropy, what kind of consideration we can make? Can we make different considerations for entropy, or can we determine the entropy values for a substance at different temperature and at different pressure? That is a question. So, this is basically we are coming to a point where we need to discuss the third law of thermodynamics. That is, if you remember, as it has already been conveyed that first law of thermodynamics forms the basis of concept of internal energy, and it basically defines internal energy and enthalpy. And second law of thermodynamics, which define the entropy, that is, it quantifies the entropy change also, and it therefore forms the basis of concept of entropy, you can say. But now, what the third law? The question arises what the third law does for us, because we already have these 2-3 functions, and spontaneity about a system we can also determine using entropy change. So, what the first law does for us? Basically, we can determine with the help of the third law of thermodynamics the entropy of a substance at a particular temperature and pressure value. Let us see how we can do that. Now, question is how to determine entropy of a substance at a pressure other than 1 bar pressure if standard entropy of a substance is known. We now consider, it means if the entropy of a substance is known at 1 bar pressure and at a particular temperature, then the question is, can we determine the entropy of substance at other pressure at the same temperature? For that, we can consider this equation for particularly for an ideal gas. So, we can consider delta as equal to Cp ln T2 by T1 minus R ln P2 by P1. If temperature is constant, it means temperature is same in the initial and final state. So, T2 T1 same. So, therefore, Cp ln T2 by T1 first term is vanishes. Then delta S equal to minus R ln P2 by P1. Now, we can modify this equation, we can take n to the denominator of left hand side, what we get? Delta S, molar entropy change equal to minus R ln P2 by P1. Now, if we say the P1 pressure is 1 bar pressure and P is the P2 pressure, accordingly we have S2 as SM and S1 as SM standard. That is, this is molar entropy at pressure P and this is SM standard, molar entropy of substance at 1 bar pressure, and these are corresponding pressure value. So, SM minus SM standard equal to minus R ln P. We can just write it this expression as R minus R ln P just by expressing pressure in bar units. So, what we will get? We will get this value of pressure, but not with units when we specify it in bar units, because 1 bar cancels. So, conversion factor need not be introduced then, because you can take logarithm of log of a dimensionless, a quantity which is not having dimension. So, therefore, the quantity SM minus SM standard is the molar entropy at the pressure P relative to 1 bar pressure. It means if you know SM standard value and if you know the pressure at which the desired pressure at which if you want to calculate SM, then you can calculate the SM value, the entropy, molar entropy of substance at some given pressure, provided you know the value of standard entropy at, that is entropy of substance, molar entropy at 1 bar pressure. But now question arises, how to determine molar entropy at 1 bar pressure? That is a question of concern. So, therefore, in order to do that, the answer comes from third law of thermodynamics. But the question arises how and what this third law of thermodynamics is. Now, if we want to understand this, we need to consider basically the constant pressure transformation of a solid from the absolute 0 of temperature 0 Kelvin to some temperature below its melting point. It means we have taken a solid substance, we have just taken a solid substance at 0 Kelvin, and at some specified pressure P, and when we transform it from 0 Kelvin, absolute 0 of temperature theoretically, to the same solid at some temperature T, the T should be the temperature which should be less than melting point, that is expressed in Kelvin, again at same pressure P. So, this is the transformation. So, it means the system has undergone a change in state from initial state where solid is present at 0 Kelvin at specified pressure and transformed to solid at temperature T. The temperature is less than melting point and at same pressure. Now, for this transformation, the question is, can we determine the entropy change? There has been a transformation we have considered, that is a solid substance it gets heated from 0 Kelvin to the temperature of interest, that is T. So, the answer to this is yes, but if you notice it very carefully, then pressure of the system is constant. So, if the pressure of the system for an ideal gas is constant, so if in the expression of ideal gas equation we can say if pressure is constant, then entropy is a function only of temperature, and ds, change in entropy, equal to Cp dt by T. Now, that is at constant pressure. So, basically it is the change in molar entropy, that is equal to St, that is the molar entropy of substance at temperature T, that is final state, there it will be, minus S naught or S0, molar entropy of same substance at 0 Kelvin, at T at T Kelvin and S0 at 0 Kelvin. Now, if you want to evaluate it, then you should integrate this equation, and within limit 0 Kelvin to temperature Tk. So, therefore, when we integrate it, we make one assumption there, Cp is either is independent of temperature or is dependent on temperature. Accordingly, we can evaluate this integral. But the question is, can we transform this equation in a way that we can take S0 to the right hand side? Then you can write St, molar entropy of substance at temperature T, that is S0, that is molar entropy of substance at 0 Kelvin, plus integral term from, that is the change, this term correspond to the change in entropy for a substance when you heat the substance from 0 Kelvin to T Kelvin. So, therefore, what you get this equation is very important equation, in a way that if you know the value of S0 or S0, what is S0? S0 is basically the molar entropy of a substance at 0 Kelvin. So, if you know the S0 and if you know the heat capacity of substance within the temperature range 0 Kelvin to T Kelvin, then what you can do is you can integrate this equation and you can determine the this contribution of second terms towards the molar entropy of substance at temperature T. So, question is, can you determine the first term S0, the molar entropy at 0 Kelvin? If you can determine it, then you can determine the molar entropy of substance at some temperature of interest, that is T. So, basically the third law of thermodynamics comes here into consideration. Third law of thermodynamics, it was just suggestion, it is just suggestion that is given by Planck. Max Planck suggested in 20th century, earlier 20th century, that he suggested that the molar entropy for a pure perfectly crystalline substance is 0 at 0 Kelvin. Why he suggested so? If you look at back to this expression of molar entropy of substance at temperature T, then what you get is molar entropy of substance at temperature 0 Kelvin. Added to this is the term from the contribution of change in entropy from 0 to T Kelvin. So, it is for sure that the entropy, since as we have just seen, we have seen that entropy increases with increase in temperature. So, it means this second term will always be a positive quantity, and entropy at any higher temperature will be greater than the entropy at absolute 0. That is, at absolute 0 Kelvin, the entropy should be least value for a substance. So, this led to the suggestion which Max Planck says that we can consider molar entropy of a pure perfectly crystalline substance at absolute 0 of temperature as 0, at absolute 0 of temperature as 0. So, with this S0 becomes 0, and that is how you can evaluate the molar entropy of a substance at specified particular temperature using this expression 0 to T Cp by T dt. But now the question arises, how to evaluate this expression? If we want to evaluate this expression, we have to make use of one of the law which relates that is de Broglie's law basically, which relates the heat capacities with that of some characteristic constants of the substances and also as function of temperature. So, therefore, in a particular temperature range. So, therefore, making use of de Broglie law, we can quantify the heat capacities and we can substitute those heat capacity expression in this expression of entropy change, and we can determine a particular value of molar entropy at particular temperature. This is the way we determine molar entropy of the substances at specified or particular temperature. So, this is how the third law of thermodynamics basically lays the foundation for determination of molar entropy at particular temperature, and that is how we say the third law of thermodynamics forms the basis of calculation of molar entropy of substance at particular temperature. So, in this lecture today what we have covered is, we had started with consideration of entropy as function of temperature and pressure. We have derived a relationship for change in entropy with for particular change in temperature and pressure for all in general, that is general expression which is applicable for all substance. Then following which we have extended the derivations which we had done for temperature and volume, for the entropy change for temperature and pressure change and temperature and volume change for ideal gases system, ideal gases, and then what we have done is, we have defined the standard state of entropy, and we have tried to observe that how we can determine the molar entropy of a substance at a specified pressure by making use of third law of thermodynamics. And if the pressure is 1 atmosphere, then what we can determine? We can determine molar entropy of substance at 1 bar pressure, and therefore, and in this way you can determine standard molar entropy of substance at 1 bar pressure, and if you know the value in this way, then you can determine the standard molar entropy of substance at other pressure. So, now the question arises, how to determine this molar entropy of substance at 1 bar pressure using Debye law. So, that will be the topic matter in the next lecture. In addition, we will also try to see what interpretation, physical interpretation, statistical interpretation of entropy has. So, with all this, we will with all these considerations and discussions, we will meet in next lecture. Thank you.
With this note, thank you sir, thank you so very much for giving us one another final session on chemical thermodynamics. I believe that all the students who might have watched this lecture would be benefited from it. And dear friends, if you have any queries, if you have any questions, if you want to give your feedback also regarding this particular lecture, then you can mail us at info.cc@nic.in. We would love to take your suggestions, and if you like to have a discussion or a lecture on a particular topic, then also you can mail us. And for viewing our lectures again and again, you can access YouTube, where we have a playlist with the help of which you can have a glimpse of these lectures on chemical thermodynamics, and very soon we are going to upload this lecture on YouTube only for you. We would be meeting again. Till then, take care. Goodbye. Thank you sir, thank you so very much.